I will be dealing with the voltage divider rule, that is for inductors and capacitors. We have already seen the voltage divider rule and the current divider rule for resistors, right? So this is the voltage divider rule, right? So if you have the elements in series, okay, these are the elements in series. If I have a voltage source Vs, then what will be this? If this is Z1, if this is Z2, okay, then what will be the voltage drop or voltage across this impedance, that is V1, that will be equal to the source voltage Vs into that particular impedance across which we are going to measure the voltage divided by sum of the impedances. Okay, that is V1. If this is V2, then V2 is equal to Vs into Z2 divided by Z1 plus Z2. So now if we consider inductor, we know that the impedance of the inductor, that is equal to J omega L. You know the formula for impedance, right? That is resistance plus you have reactance. X is your reactance. So of the pure inductor, resistance will be equal to 0. That is for the pure inductor. So the impedance of inductor is purely imaginary. That is nothing but X is equal to omega L. So Z will be equal to J omega L. So now I will substitute here. So if I consider two inductors L1 and L2, okay, two inductors I will consider, that is in series L2, and if we consider this as voltage V, this is V1 and this is V2, okay, I will consider the current flow in this direction. So here Z1 is nothing but we can say V1 is equal to V into, what is Z1? It is J omega L1 divided by J omega L1 plus J omega L2. So V into J omega L1, taking J omega common, we have L1 plus L2. So J omega cancels. So V1 is equal to V into L1 divided by L1 plus L2. So when the inductor is in series. So this is similar to the voltage divider rule of the resistors, right? So VR1, that is equal to V into R1 divided by R1 plus R2, sum of resistances. Similarly for L1 also, see if you have L1, voltage into that particular inductor where we are measuring the voltage divided by the sum of the inductors. Similarly, V2 can be written as V into L2 divided by L1 plus L2. So this is the voltage divider rule for the inductors. So now let us consider the capacitors. What is the impedance of the capacitor? That is also purely imaginary because the resistance of the pure capacitor, that is equal to 0. So R is equal to 0. So Z is equal to, we have J divided by 1 by J omega C. 1 by J omega C. Or we can also consider this into J divided by J. So that will be J square will be equal to minus 1. So minus J divided by omega C will be your impedance for the capacitor. Okay, so if you have two capacitors which are in series and you have a voltage source V, the current direction is this. Here we have V1 and this is your V2. This is the capacitor C1 and capacitor C2 which is connected in series. So now we have to measure V1 and V2. We know the formula V1 is equal to V into Z1 divided by Z1 plus Z2. Now I will consider this formula, okay, that is minus J divided by omega C1, that is for the C1 capacitor, minus J divided by omega C1 plus minus J divided by omega C2. Okay, so this can be written as, so minus J by omega, if I take it outside, that gets cancelled, right? Then we are left with 1 by C1, then we are left with 1 by C2. This gets cancelled. So it is V into 1 by C1 divided by 1 by C1 plus 1 by C2. This is your V1. Now let us simplify this. So V divided by C1, here it is C1 plus C2 divided by C1 C2. Okay, so C1 gets cancelled, this C2 goes up, so it is VC2 divided by C1 plus C2. This is your V1. So if you are measuring the voltage across the capacitor here, that will be the voltage into the capacitor, that is another capacitor present, not across which we are measuring the voltage, but it is another capacitor divided by the sum of capacitors. So we can say if you had this one resistors, this is the current divider rule, this is R1, R2, this is I1 and this is I2. So if I want to measure the current across this resistor, that is current through this resistor, that was equal to I into the resistor present in the another branch divided by R1 plus R2, right? So similar to this current divider rule, we have the voltage divider rule for the capacitor, that is voltage into the other capacitor value divided by the sum of capacitors. So current divider rule for this will be reverse of this, means it will be the voltage divider rule which is applicable for the inductors and the resistors. So we know if this is the impedance Z1, this is impedance Z2, this is voltage V, then we can say if this is resistor, if Z is equal to R, then V1 will be equal to V into R1 divided by R1 plus R2. V2 is equal to V into R2 divided by R1 plus R2. If the impedance is, means if you are considering the inductor, in that case, okay, if that is Z is equal to J omega L, then V1 will be equal to V into L1 divided by L1 plus L2. V2 is equal to V into L2 divided by L1 plus L2. But if Z is equal to minus J divided by omega C, that means if you are considering the capacitor, V1 will be equal to V into C2. See, it is similar to the current divider rule of the resistor, divided by C1 plus C2. V2 is equal to V into C1 divided by C1 plus C2. Here we have same V2, L2, but here we will be having different one for the capacitor. Okay, so this is the voltage divider rule for the inductor and the capacitor. Now let us consider the current divider rule for inductors and capacitors. So you know, if there is a current source I, and here we have impedance Z1, and here we have impedance Z2, then I1, this is I1, this is I2. Then what will be I1? That is total current into the impedance which is present in another Z1 divided Z1 plus Z2. Okay, similarly I2 will be equal to I into Z1 divided by Z1 plus Z2. So in case of resistors, we know Z is equal to R, that is resistance value. So we have I1 is equal to I into R2 divided by R1 plus R2, and I2 is equal to I into R1 divided by R1 plus R2. This we have derived in the one of the videos, so I will not derive it again. Okay, so what if I consider inductor, that is which is having the pure imaginary, that is reactance, right? So pure imaginary impedance Z. So if we have this one as inductors L1 and this is L2, and we have a current source here, that is I, this is your current I1 and this is I2. So we can substitute in this, right? I1 is equal to I into J omega L1 divided by J omega L1 plus J omega L2. So taking J omega common in the denominator, we have L1 plus L2. I into J omega L1. So J omega gets cancelled. So I into L1 divided by L1 plus L2. Sorry, it is Z2. So it is L2. I into L2. So it is similar to that of the resistor. So instead of R2, we have L2. Everything is same for the inductor and the resistor. So now if we consider capacitor, okay, if we have capacitor here, and if you want to find the current through the capacitors C1 and C2, so in this case, if I apply, that is Z is equal to minus J divided by omega C, so I1 will be equal to I into, this is minus J divided by omega C2 divided by minus J divided by omega C1 minus J divided by omega C2. So if I take minus J divided by omega, so this gets cancelled, right? Minus J by omega. So we are left with this. We are left with this C2. So now we will simplify this particular thing. So it is I divided by C2. Then we have C1 plus C2. Then divided by C1 C2. So C2 gets cancelled. So we have I into C1 plus C2. This is your current I1. So this is similar to the voltage divider rule for the resistor and inductor, right? So that is current through this capacitor, that is equal to total current multiplied by that capacitor only through which we are measuring the current, divided by the sum of the capacitances. So we have voltage divider. See, just remember voltage divider rule for inductor and resistor, that will be almost equal to the current divider rule for capacitor. Okay, so if you have current divider rule for inductor and resistors, that is nothing but voltage divider rule for the capacitor. So you have to remember this. For capacitor, you will be having the reciprocal of these two. Okay, current divider rule, it will be for voltage, and voltage divider for these two, it will be current divider rule for the capacitor.